The electric flux or constant electric fields. To calculate the electric flux, we use the following. We say that the flux is the integral, and the loop here means over a closed surface where I have E dot dA. And this is broken down into two categories. If the electric field is a constant, then the integration leads to a flux that's just E dot A. And of course, because of the dot product, it's E cosine of theta, where that is the angle between the electric field and the area vector. If E is not a constant, then we have no choice but to integrate E dot dA. We're only focusing on uniform fields, constant fields in this part. So let's go focus on that. We start, so if you're looking at the flux, the A vector plays a big deal. So let's go look at that. We start by first defining the area vector. So the area vector can be broken down into similar unit vectors as we deal with Cartesian components. That is similar to Cartesian unit vectors, where we have I hat and j hat. A vector can be written as r equals to rx in the I direction plus ry in the j direction. Now, if we apply the same thinking to an area vector, so applying this thinking to the area vector, area vector A, we want components that are parallel and perpendicular to the electric field. So in other words, so when I'm thinking about an electric field, picture-wise, I imagine that I have a field that's coming, let's say, straight like this. So if I'm looking at a dot product between these two, then I have to imagine that I have an A vector that's looking like this. So now we could come in here and we can define this angle theta between these two. So when we talk about parallel and perpendicular, that means we're picking this relative to the electric field. So now we can define what we're talking about. So if I say the definition, here's my definition. The area vector, and this is tricky here, is normal, which also means perpendicular to the surface. Okay, so I got to be careful with the language. So when I'm thinking about this, this is what I'm thinking about. I have a vector A, and it has a magnitude, and then I have this normal vector. And then this guy has components A parallel and A perpendicular. So that means that these guys are actual components that have their own directions. And we'll define this where n hat is the normal unit vector to the surface. So picture-wise, what am I imagining here? So if I think about a picture, I could imagine that I have a rectangle. It's going to look like something like this. So the question is, I have to think about an electric field. So I imagine that I have an electric field that's moving in this direction. If I'm going to look at the dot product between E and A, I need to know that direction of the electric field. So then here we go. This component, so saying that, let's say that this is the center of the surface, I'm going to have a component of the vector that I call A parallel to the electric field. So then that here is my parallel unit vector axis. On the other hand, I'm going to have a vector that's perpendicular to the direction of the electric field. So that's going to be A perpendicular. And so if I look at this, that gives me the perpendicular field or perpendicular axis, which I did not write correctly there. So let me go back and correct that. Perpendicular. So now I want to show what actually happens if I have a vector now. So in this situation over here, it turns out that if I take the exact same thing now, and what I'm going to do here is that I'm going to lean this guy. So I'm going to take this and I'm going to lean it. And let's say that I lean it something like this. Then I'm going to go down, let's say something like, nope, 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 nope. That's not the way I want to draw it. I'm going to draw it like this. So what you're seeing here is that I've actually leaned this back. And so you're seeing here that I've now changed the angle of the plane. And now I'm going to focus at this vector right here. So if I look at the electric field again, we see that the electric field is coming in this direction. So everything has to be measured relative to that direction. So if I look at this thing, then I see that my surface has a vector that can be represented in saying that this guy is popping out at an angle. And this is the area vector, which is A n hat, because that's the vector that's perpendicular. But now I can decompose this vector by calling this the A parallel axis, and I can convert this vector and calling this guy the A perpendicular vector. So now I can write this vector that now reads something like this. So I now have a vector that is going to be a vector, which of course could be A n hat, But if I decompose this guy, this is what I see here. I see I have A parallel and I have A perpendicular. And that's what my area vector is. And something I did not mention, this is the angle between parallel to the E field and the vector A. So again, this is for a plane surface tilted at an angle. Well, now we just start to look at the flux. So what do we know? The flux is a measure of the number of field lines poking through this surface area. Remember, it is the vector dot product that tells the flux how it is going to behave. And what I mean by that is that when I look at the flux, it's E dot A, but this is really E times A cosine of theta. So right away, you can see here is that this is angle dependent. So the flux depends on angle. So what I'm going to do here is that to help with the visualization, I will use the Duffy Flux app as a guide. So here I go. So this is Duffy's electric flux. And anything that I use here, like this in lecture, you know that it's in the lecture page so that you can go and do this. So it's the same question that I started off with, but the question is this: how does the flux behave as theta varies? So how's it going to change as an angle, as the theta angle changes? So the first thing that we want to look at is that we want to look at theta equal to 0. Okay, so let's go look at the applet. I'm going to go and share my screen. So what I'm seeing here is that you're probably seeing this thing, and look at the angle right there. You could see that it's the angle 0. So what you're seeing here is that this is the rectangle from a side view, and you could see that the blue here represents the electric field. And then you have a little tiny black line with a red dot that represents the area vector. And what you're seeing here is that if I have an angle of 0 degrees, and I have this setup, then what this is telling me here is that according to this, you have a maximal area, and that maximal area is then giving you maximum amount of flux. So if I count the dots, you could see this is 5 by 5, so there should be 25 field points. So I just took an image of this thing. Let's go back to what we were just looking at. So what I'm seeing is that I'm seeing this. We're looking at theta equal to 0, and then here is the image that I just got. So what do I see about this image here? So what I'm seeing here is that I have a side view, and when I'm looking at my side view, I'm seeing that this right here, I have this flux like this. So this is my rectangle, okay? And so when I'm looking at this rectangle, what I'm seeing here is that I have these E fields. So what are the E fields doing? They're coming in, and then they poke through the surface. Now, I'm not going to draw all 25 lines, but we have a field that's going there. Now, when I look at the area vector, and you could see the area vector right here, right? This is the area vector right there. You're seeing here that I have an area vector that then is going to be in this direction right there. So I'm seeing the electric field, and I'm seeing the area vector. So when I look at the flux that's coming through this thing equals, if we do the counting right, there's 25 lines poking through. Okay. So then what this tells me here is that if I apply the equation for the flux, then this will then be EA. But now this angle, as we can see right here, we can see that this angle is 0. That angle is 0. So I get that E and A are fully projected onto each other. And this gives us max flux. So right here, so when I'm looking at this guy right here, at this thing, we're finding here that we get maximal field lines poking through this rectangle. Or square, maybe I should say square. In other words, the E fields see maximal area. So they're seeing this rectangle. So now let's go to the next one. So in this situation, I'm now going to go to the other extreme, and I'm going to pick a second situation where I'm going to say theta is equal to 90 degrees. So now let me go share my screen. And I'm right here. So now I'm going to change that angle, and I'm going to go to 90 degrees. And now look what's happening here. You'll see that the field lines only see a line. There's nothing that actually can go through this rectangle here. And so this is literally reading, zero flux. I don't know what that number means right there because we're not actually seeing the whole number, but there's zero flux here. That should be saying zero. So let's go take this back. And so now I'm just grabbing the image that I just took here, and this is what I'm seeing here. So when I'm looking at this guy, I see this. I can see right away that this is my angle is going to be this guy right here. This is my angle here. And look at the area vector. It's perpendicular to the surface. So if I'm looking at this thing, what I'm seeing is that I see this. I now have my rectangle, and it's right here. Now remember, this is infinitely thin. It's a line. So when I'm looking at the fields, what are the fields doing? They can't go through the square. And because they can't go through the square, that immediately tells you that you have, just following up here, if I look at the flux of this thing, I'm going to have 0 lines poking through. So according to this, if I look at the flux, this is really EA, and this would be cosine of 90 degrees, which of course is 0. So I get 0 flux. So nothing is going through that rectangle. So if I look at this guy right in here, you could see that that's exactly what it's saying. It's saying no field lines can pass through this square. So that's what we mean by 0 flux here, right? So again, this is the only situation where you get 0 flux. And then I'm just going to pick some arbitrary angle. And in this angle, I'm going to say this is 0 degrees. Theta is somewhere between 0 and 90. So what I want to do is then again go back and look at the screen share. And now what I'm doing here is that I'm going to pick some angle. So now what you're seeing here is that I now have tilted my rectangle or square, and you could see that the normal vector is perpendicular to the surface. So if I go and I copy this and bring it into here, here's what I'm looking at. So I have this now. So the first thing that you want to pay attention to here is that now let's look at my units. This guy right here is my area vector. Let's say that this is my area vector right here. But I have two components. One component of the field tells me that the area, this is a parallel. And then there's another unit vector that goes perpendicular to the field lines, and that's a perpendicular. So these are the vectors that we're talking about. So when I look at the tilt of this guy here, you can see here is that right here, this is the angle theta that we're talking about. Now, if I compare the number of field lines, This is 3 times 5, so that's 15 lines. This is 0, and then this guy is maximum at 0 degrees because it's 5 by 5, so this is definitely a smaller one. So if I look at this thing, picture-wise, this is the thing that I was trying to draw earlier. So now, if I look at this guy, this is, again, a side view. The way I drew it earlier is that I did this. I said, suppose I have a rectangle that looks like this, and then I tilted it off to an angle. So now the same type of thing is happening. So if I have an E field, what I'm seeing here is that I have a perpendicular vector. So in this case, I have a perpendicular vector, a normal vector. I don't want to confuse that. And because the electric field is coming in this direction, then what I'm seeing here is that I have a smaller component here, and that's a parallel. And here I have a smaller perpendicular component, which I'm going to call a perpendicular. And that's exactly what I'm doing right here. So when I drew it, I was talking like this. So these two are exactly the same situation. But now we're talking about, what am I seeing here? Well, when I look at the electric field, note that the electric field is coming in. You know what? I think I'm going to redraw this picture because I spent time with the areas. So I'm going to copy this and bring it down. And the only thing I care about is I only care about the normal vector. So when I'm looking at this, you're seeing here is that if I have the fields are coming through. And so these are the electric fields, and they see a smaller field value because they see a smaller area. So what you're seeing is that right in here, the field lines see a reduced area. As lines poke through. In other words, you get a reduced flux. So if I count my numbers, I'm going to say that in this situation, my flux lines is then going to be, it's 3 by 5, so it's going to be 15 lines of outward flux. So now the last thing here is that let's just summarize everything that we did. Okay, so let's look at this thing mathematically. And it goes like this. So mathematically, let's summarize the flux. So we then say that the flux we defined as this, and this guy is E dot A which is EA cosine of theta, where n hat tells me the direction. That says that it's a plus sign or a minus sign if it's out. So it's poking out. How do I say this right? So it's poking out of the surface. If it's poking in the surface, then we give it a negative sign. So that is, in essence, another definition of the flux. And here are the units. So the units, it says here that a unit of flux is equal to a unit of electric field times a unit of area, which will then be a Newton meter squared Coulomb. That's the units. So in summary, we say this. 1, we had an angle pendant. So if I summarize this thing, here I go. So in this situation, the electric field is coming through and it's poking out of the surface. And then the area vector is going to be normal to the surface. It's going to look like that. So if this is the case, then this tells us here is that theta here is 0 degrees. I can do the same thing for the angle equal to 90 degrees. So then here I have and so as I'm looking at this thing, what do I see? Well, what you see here is that there is no field that's going through that rectangle. So in this case, we then say here is that this is the direction of the E field. But the area is perpendicular to this. So if this is 90 degrees for the area element, then I know that flux is going to be 0. So in this situation, we said that in here, we said that the flux EDA of cosine of 0, that gives us maximum. Maximal exposure, if we want to say. So this gives max flux. Now, in here, that flux is then going to be EA cosine of 90, but we all know that the cosine of 90 is 0, so this becomes a 0 flux. And then finally, if I have an angle between 0, theta, and 90 like that, then I have a tilting rod or rectangle, excuse me. So when I'm looking at this case here, and I have flux lines like this, or you could see here is that then this flux goes like that. And so the upshot is this. There is an effective area dependence. So if I have an effective, so if I increase the effective area, that tells me I have more field lines poking through. So therefore, it increases the flux. On the other hand, if I do the opposite, if I decrease the effective area, then there's going to be less fields poking through the surface. And therefore, it has to decrease the flux.